discussing diodes. Okay, so I think some students have told me they have some doubts regarding the the V output versus V in waveform, or the current versus voltage waveform. So I'll be discussing a brief about those waveform. Uh, okay, so before that, I want to give you an idea about the transistors. Okay, so we will discussing waveform. Before that, I want you to. I already discussed before that, like a diode, we are taking a black box concept. Like whenever diode is having a anode positive and cathode negative, it is on or is conducting, right? We already discussed. I'll just so we'll discuss only diode whenever there's a current flow from higher potential, lower potential, or higher height, lower height. Diode is allowing the current flow, water flow to it. So it is like a unidirectional valve. Okay. Similarly, we need to develop a concept of transistors. Okay. So this is a unidirectional valve, and reverse, it is not conducting. Okay. So this is a black box concept. Although practically, when we deal with diodes, there is some non-idealities like voltage drop is there, some power dissipation, some voltage dissipation is there, resistance is there, etc. So although right now we don't need to bother about that because it is approximated to be negligible. So today I want to discuss you the concept of transistors. We already discussed the transistors. Uh, we already discussed transistors as a pipe, right? Best analogy of transistor is like pipe. Okay, so pipe has what? The input water reservoir. Okay, the water is coming from a reservoir and it is coming to the pipe. Okay, now there's a control. There's a control portion using which we can control the flow of the water. This is control portion. This is control valve. Okay, this is the control valve portion, and based on the control valve turning of the control valve, or input giving to control valve, I can control the water flow through the output of the pipe. Okay, so this is basically we have discussed transistor modeling, simple black box concept of transistors. Okay, black box concept transistors. Now, now I want you to have feel how transistor works in real life. So for this, I'll take a simple transistor. It's called MOSFET. Okay, metal oxide semiconductor field effect transistor. Okay, we'll take an example of MOSFET. Metal oxide. So you just assume you should understand it's kind of MOSFET. It's like it's kind of transistor. Other transistors are we have BJT, which you might have learned in your undergrad PG, like pre-degree courses like BJT, which have collector, emitter, drain. So another type of transistor is MOS. Okay, so MOS is drawn like this. It's called M and MOS. Okay, similar thing. Like it has a base of BJT corresponding. There is a gate of this MOSFET, and there's a drain and source. Okay, right now it is like a black box concept. We don't need to worry about this. I will come to it. Okay, so but you should understand that we are going to have a black box concept of a transistor. We are focused on how the transistor works. Okay, and this can be compared to a pipe or a tap, where there's a input flow of water is coming, and based on the control tube or valve, we can control the output through the tap. So similarly, transistor is like a current is flowing through one terminal, and another terminal is going to gate terminal or control terminal used to control the flow of the electrons or current through the output valve. Okay, so this concept is required. Now we go for this MOS concept. So I'll just tell you some rules. Based on that rules, you just need to know the or experience or feel or analyze the working of a transistor. Okay, so first I will tell you we are dealing with MOSFET. Okay, MOSFET, MOSFET. Okay, okay. So right now we are acting a simple principle of transistor acting as a switch. So these two things we are combining: concept of MOSFET and action of transistor as a switch. As a switch. Okay, should be very clear what we are dealing with. This is a simple application of transistor as a switch. Okay. Now, now the transistor as a switch is ideally like a tap, which is used for only onning and offing the water flow. Okay, right? There's a there's a tap here. The water flow is coming here, and there's a control C, and based on the control can be 1 or 0. Okay, there's some input I can give to the control terminal of the tap, If I make it press it, it is on, water is coming through the output. If I press it off, there is no water flow. Getting? Very simple. Okay, so this is the minimum thing you have to understand. We are comparing the transistor as a tap versus a control terminal, and just pressing or oning and offing is control is possible. If I on it, there may be water flow. If I off it, there may not be water flow. Simple. Okay, so this is the transistor switch. Transistor is having a different applications like amplifiers, filters, and different applications are the. But here, for a simple case, taking for an entry level understanding, we're just taking the application of transistor as a switch. Okay, so we know it's a tap. There is an option of oning and offing, and based on the control terminal oning and offing, or 1 or 0, or high voltage or low voltage, I'm able to control the water flow or the current flow. Okay, let's see more about MOSFET. Okay, now MOSFET, metal oxide semiconductor. You don't need to worry about the name. You just understand this is some kind of a transistor. That's it. We'll go deeper about the MOSFET structure, its operation, application, etc. Later. Okay. Now I'm just drawing a MOSFET diagram. Okay. Now one gate is gate, or a control terminal. You can say gate. There's a drain. There's a source. Okay. Now I'll just tell you that based on our uh, abstraction or simplification idea, whenever my gate voltage is 1, I got VG. Okay, I got VG. If VG is greater, sorry, okay, this is my transistor. Okay, now this is some gate terminal, drain, and source. Okay, now if I say VG is equal to high, I call this transistor is on. Transistor is on. Okay, and again I say if VG equal to low, transistor is off. Getting? There are two concepts I'm saying. It's a simple transistor I'm saying. There's a control terminal called G, or gate, in within the transistor. Control terminal C. Okay, and which connects the input and output. If control terminal voltage VG is high voltage, then the transistor is on. What is the meaning of transistor on? The drain is short circuited to source. Clear? And if control voltage is low, that means that means yeah, when the control voltage is low, the drain is not connected to source and the transistor remains off. Clear? Now I call the name. I'll just tell the name of this transistor. This transistor is called NMOS, N-type MOSFET. Getting? Very simple. We have BJT, two types of BJT we already discussed in first class. That is, one BJT is NPN BJT and there is PNP BJT. In one NPN, I have two N type of semiconductors and one P type semiconductors. And PNP transistor BJT, there are two P type semiconductor, one N type semiconductor. In N type BJT, NPN BJT, majority carriers are electrons. In PNP BJT, majority carriers are holes. Likewise, exactly same in NMOS, the majority carriers are electrons. N-type MOSFET. N-type means electrons are the majority carrier. You should just remember that on the N-type NMOS. N-type carrier. Electrons are the majority carrier. So basically, electrons conduct the volt current. Okay. This is so. Right now, what I explained is the working of NMOS. Okay. So this is the diagram of NMOS. We have a drain and we have source. Okay, we have a drain terminal, we have a source terminal, and we have a gate terminal. Okay, and gate terminal is a control terminal which controls or decides whether the transistor is on and off. And what is the control table? If VG or control voltage is high, the transistor is on. What is the meaning of transistor on? The drain and source are connected. There's a current flow or transistor is on. Okay, and if VG or control voltage is low, transistor is off. That means drain and source are not connected, disconnected, high resistance, infinite resistance, or whatever. Transistor remains off. Okay, very clear. Now, I'm just again I want to describe you another type of transistor. It is just dual or opposite of NMOS. That is how to make this. This is everything remains same. This is drain, this is source, and this is a gate terminal. The only difference is just a bubble. We draw a bubble in the gate. Okay. So what is simple idea? Bubble means you remember what is bubble? This is AND gate. This is AND gate. When we keep it bubble at the output, it is called NAND gate. This is inverted AND gate. Similarly, if we keep if we invert or bubble at the end of a OR gate, it becomes NOR gate, right? Getting? So same concept. I'm telling this is a PMOS. This transistor which I'm just drawn here is a PMOS. The terminals are exactly same. We have a drain, we have a source, we have a gate, but the input towards the gate, input given to the gate is just bubble to go into the control terminal. Okay. Now I'll just write the name of the transistor. It's called PMOS, P-type MOSFET, P-type MOSFET or P-type MOS semiconductor device. Okay, so transistor. Now let me write the conditions of working of the PMOS. Now I will tell PMOS will work when VC or VG is VG equal to high. What happens? Just inverse of NMOS. VG equal to high, my transistor remains off. Getting? Just opposite of NMOS. And if gate voltage is equal to low, that means I'm giving very low voltage in the input or control terminal, then the transistor remains on. Getting? Or I can say, if my gate voltage is 1 or high, means 1 means digital 1, high, transistor remains off. Okay, same. And if the gate voltage is 0, that means low voltage or 0 digital binary mein, then transistor remains on. Clear? I think everyone got this simple abstraction. We have two type of MOSFET, NMOS and PMOS. Okay, I'll just again consolidate. This is NMOS, okay, and this is PMOS. Okay, so both has terminals, both are terminals, identical terminals. Drain is at the top, source is the bottom, and gate terminal is in the control terminal. Again, in PMOS also, drain terminal is the top, source. Even drain and source are interchangeable. You don't need to worry about drain and source. Both are interchangeable because it is symmetrical, right? That means you don't need to worry about the both are same. You don't need to worry interchangeably. Both are symmetrical. Okay. So right now very simple. Both are a type of transistor like a tap which have a control terminal, and based on this input to that control terminal, my transistor is on and off. Okay. If in the NMOS, if the input is high, it is on. Okay. And input is 0, it is off. Clear? And similarly in the PMOS, what happens? Input is low or 0, it is on. Okay. And if the input is high, it is off. Clear? Very simple. So this is called N MOSFET, N type MOSFET, NMOS transistor. Okay. And this is called PMOS transistor. Okay. P-type semiconductor. Majority pairs are here holes and here electron. This is exactly the similar to what we already discussed. It is exactly like NPN. This is NPN transistor, NPN BJT. Okay. I drawn the left top. And